Hey everybody, we're continuing our lectures on carboxylic acids and carboxylic acid derivatives. It's chapter 19, carboxylic acids and derivatives. And so this is a continuation of our last lecture, which is also in chapter 19. And we're getting into something called carboxylic acid derivatives. So kind of the second part of this. First we're talking about carboxylic acids, then we're talking about the derivatives. Carboxylic acid derivatives. And this is section 6. This has this kind of addresses a whole bunch of compounds that sort of have this sort of structure with a leaving group on a carbonyl, a leaving group, and the leaving group ability kind of varies from derivative to derivative. So we'll have really good leaving groups and really bad leaving groups. What we're going to learn about is kind of how to interconvert these guys. And this will be a major topic of this section, number 6, is how to interconvert them, what they are, and how to interconvert them, and what all of the reactions are. So you're going to learn a ton of reactions, and a lot of them are similar. So if you are doing index cards, it's great. You'll just have a stack of index cards related to these reactions, and maybe put a paper clip on them and keep them organized, because there's going to be a lot of these different reactions. Fortunately, there are some consistencies with them. So let's go through the derivatives first. First one is acid chloride. And me putting it on the left, I'm going to imply that this is the most reactive of the ones we're going to learn, and is the best leaving group. We know chloride as being a really good leaving group, right? So not too surprising, it's going to be the most reactive. And chloride's a really good leaving group. Why is that? It's because it is very electronegative when it falls off. It's very electronegative, okay? Okay, and what's our next one? So we're going kind of in order from most reactive, best leaving group, to least reactive, worst leaving group. Next one, looks like this, and this is called an anhydride. Anhydride. So it's kind of, it's similar in reactivity as an acid chloride. The idea, though, is rather than chloride being a leaving group on the carbonyl, it's kind of like this whole right side is a leaving group. So we'll see how that works in reactions in a bit. But anyway, that's what anhydride looks like. And then next up is an ester. You've learned about esters. You at least know what the functional or the atomic arrangement is for an ester, right? Okay. Trying to get the contrast a little better. Okay. All right. So yes, that's what an ester is, right? Okay. What's the next one? And I'll zoom out and show all of them in a second. Next one is kind of like an ester, but it's got nitrogen in it. It's an amide. Okay, and it's a little less reactive than an ester. And then we got our good friend, the carboxylic acid. So it's kind of the least reactive of all of these guys. Okay, so it's really good to memorize this order Maybe you have an index card that shows this order. Also have it nicely in your notes. Got to know the order. And so if the left is the most reactive, best leaving group, the right is the least reactive. And when you think about the leaving group, what's the leaving group? It's the hydroxy. The leaving group is the worst leaving group. Worst LGs, the worst leaving group, okay? All right, so we'll say the remainder of the chapter is kind of dealing with the interconversion. Actually, the remainder of this chapter and a lot of next chapter even is interconversion of carboxylic acid, derivatives. So it's interconversion of carboxylic acid derivatives. Okay? There's a lot of redundancy. Lots of redundancy. That doesn't mean you don't have to learn it. It means that we're going to try to organize this in a way so that you see the redundancy and learn some general principles, and then we use those over and over. Okay? Cool. Most of the reactions we're going to learn are going to be related, so that's great. There's going to be a lot of similarity between the different reaction mechanisms. Okay, so we're still on number 6, and we're going to learn right now learn 2 general mechanisms. 2 general mechanisms that are going to apply to a ton of these reactions. So, first one is going to be something called acid catalyzed NAS, NAS. So your first question will probably be, what is NAS? And NAS is nucleophilic acyl substitution. Nucleophilic acyl substitution, which is going to be kind of like, you know, all of the reactions we're going to see in this chapter, and a lot from next chapter, will be of this variety of nucleophilic acyl, 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 acyl substitution, and it's going to be conversion of one derivative to another. So let's show an example. This is acid catalyzed NAS. Okay, so I have one of these things. It can be any of the ones we just showed. And we are going to, this is usually going to be reversible, react it with, kind of, in very general terms, acid H plus nuke, H plus nuke. Okay, that's easy. What do you think the first step of the mechanism is? Whenever you have acid and you have a carbonyl, usually something happens where you protonate the carbonyl, right? And what does that give you? A protonated carbonyl. Whoa, and I messed up. I said nuke, I should have said LG, so my bad. Okay, so take a step back, it's leaving group, right? Yeah, okay, so we protonate the thing with the leaving group, right? Okay, and it's an RSCC now, right? Let me step ahead on the product, nuke, leaving group. That's where we're going, right? Okay. So we're converting, essentially, we're kicking off the leaving group to make the nucleophile. Okay, so in resonance, you can just imagine that, right? So it's a resonance, you have a carbocation, it's an RSCC, a resonance stabilized carbocation. What do you think the nucleophile is going to do to that carbocation? It's just going to attack it. Right? The nucleophile attacks the carbocation, and now I'm going to change this slightly, and I'm sorry to do this, but I'm going to add assume a proton was on the nucleophile, because usually the nucleophile has a proton on it. So let's just change this to H-nuc, because it's usually like an alcohol or something, and let's just change that. Sorry. It was in my notes, and I didn't look at my notes. So there we go. And then we'll do it in the beginning too. Let's change it to the very beginning. I'll show you it when we're done here. So I'm changing, there we go. Okay, let's start from the beginning again. So the thing with the leaving group is any of those derivatives reacts with acid plus and H-nuc ... to give the final product carbonyl nuc and then the leaving group, okay? All right, and the first step was protonation of the carbonyl, so now we have an RSCC, protonated carbonyl, right? And RSCC, and then H-nuc attacks that, so it forms a bond from nuc to the plus charge. Now H-nuc is positively charged, right? And what happens next, and what usually happens after nucleophilic attack, is transfer of a proton, usually from one atom to another. So we're going to assume transfer from the nuc to the leaving group. Now the leaving group has a proton, an extra proton on it. It's maybe a better leaving group. Now we kick it off with the oxygen. Cool? Alright, so the oxygen kicks off the leaving group. What does that give us? Essentially the product. And then leaving group as in that's fine, whatever. Okay, and then loss of a proton, minus H plus. And there we go. So this is kind of a general idea what the mechanism is going to look like. All right. So we have, it's called acid catalyzed NAS, H plus or acid catalyzed NAS, where we protonate the carbonyl, nucleophile attacks, proton transfer, PT, right? PT. Proton transfer from the what was the nucleophile to what's becoming the leaving group. Leaving group gets kicked off, loses a proton, and we're done. This is a new mechanism. You've never seen this before. Okay? This is called acid catalyzed NAS. Now let's do the base mediated NAS. It's not catalyzed. Let's call it base mediated NAS. So this is another type of NAS we're going to see. What's NAS again? It's nucleophilic acyl substitution. Nucleophilic acyl substitution. Okay? Okay, so let's show what happens in a base mediated NAS. This is a lot easier. I don't need as much space for this one. Okay, so for the base-mediated NAS, the nucleophile just attacks. The nucleophile just attacks. Base-mediated NAS. Nucleophile just attacks. And what does that give us? Nuke still has an H on it. And a charge maybe? Where's the charge? The nuke is plus charge, right? So, okay, nucleophile attacked, electrons go up, O minus, nucleophile is still charged, it's got a positive charge now. It was neutral, now it's positive. What do you think the base is going to do? The base might do what bases like to do. Maybe take a proton off. What is the nucleophile? That's what it's going to do. I'm going to draw it over here. B dot dot, circle. Okay, sorry. It's a little congested, but we got this. Base takes proton. And give the electrons back to nucleophile. Okay? So base takes the proton and gives the electrons back to nucleophile. Okay? And we're basically done at this point now. So the base now we got R O minus leaving group. In this case, now O minus swings down and kicks off the leaving group. Okay? So this doesn't need protonation on this leaving group, and because this will happen for the really good leaving groups, we'll say, like chloride. Chloride is an amazing leaving group. It can't get protonated anyway. But what I'm trying to show is that, yeah, there's going to be two general mechanisms. Okay, we'll zoom out and show the base-mediated NAS again. Nucleophile attacks. Base takes proton. Base takes proton, right? And then O minus swings down and kicks off leaving group. Very easy, right? So it's like first step, second step, third step. It's 3 steps. The acid catalyzed NAS is a little bit more work. Protonate the carbonyl, make an RSCC, nucleophile attacks, proton transfer, kick off the leaving group, lose a proton. So there's a little more work to the acid catalyzed NAS. Gotta know both though, and we'll see them both, okay? Acid catalyzed NAS, base mediated NAS. Why is the top one called acid catalyzed? What's catalytic here in terms of acid? Acid catalyzed NAS. Well, we're grabbing a proton initially, we're losing a proton at the very end. At the very end, we have an extra proton, we lose it. That's why it's called acid catalyzed NAS. It's catalytic, right? Catalytic and dependent on acid. Base mediated, why don't we call this base mediated NAS? Sorry, why don't we call it base catalyzed NAS? And the reason is we're actually consuming base. It's not like we're using it and regenerating it, right? So we're actually using it up. So this attacks, base takes a proton, and then the leaving group gets kicked off, right? So it's not a catalytic process the way the top one's a catalytic process. Okay, so what are our two reaction mechanisms? Acid catalyzed NAS and base mediated NAS. Okay. Okay, so let's show two simple examples of this now. Two simple examples. The first one There's an acid chloride. There's an acid chloride. And we're going to react it with an amine. Propylamine, so there's 3 carbons. Carbon, 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 right? Propylamine. Carbon, carbon, carbon. H2N, 3 carbons. And we're going to use a base. And the base is usually, for all these reactions, pyridine. It's pyridine, right? And if we were going to give pyridine a abbreviation, sometimes we say PYR dot dot. PYR dot dot. Well, anyway, that's the base. And sometimes you just say B dot dot for base. Or we say PYR dot dot. Or we say pyridine. Pyridine has a lone pair on it right there. And it's just a mild base that's really good for these acylation reactions. It is very stinky, and it also causes sterility in men. So anyway, yeah, it stinks really horrible. so maybe someday you'll have the pleasure of smelling pyridine, and you'll think about how I told you how bad it stinks. Okay, the product is an amide. Okay, so this is a pretty easy example of a NAS reaction. Is this a base-mediated or acid-catalyzed NAS? What do you think? Well, we have base present, so it's maybe a base-mediated one. And so that's going to... What was the first step in the base-mediated NAS? Nucleophile attacks. That's the first step. Nucleophile attacks without help. Nucleophile attacks. What does that give us? It gives us this, right? Okay. All right, so we have a 3-carbon piece right there. What was the next step of the base-mediated NAS reaction? Oh yeah, do we have a charge somewhere? As neutral plus neutral to make an O minus, and something's got to be positive, so it's positive like that. Okay. All right. Sorry. And a little bit of a glare on the paper, and I'm trying to eliminate that by positioning my light. Okay, so how it may be better. Yeah, so 3-carbon piece on the nitrogen. So we have this O minus N plus. What was the second step in the base-mediated NAS reaction? Base takes proton. So now the base just takes the proton, and I'll just circle B dot dot, attack proton, take the proton, put it on nitrogen. Okay, now the O minus swings and kicks off the leaving group, and we are done. So I said this is a simple example. I hope you agree this is a simple example of how the acid chloride reacts with an amine, presence of base, to do a base-mediated NAS. Nitrogen attacked, electrons go up, electrons, and then the base takes the proton, and then electrons go down, kick off the leaving group. This is a pretty easy example, okay? So this works wonderfully. Good reaction. We'll show a bad reaction now. Why did this work so well? We have a great leaving group. Chloride's a wonderful leaving group, okay? And And with chloride being a good leaving group, it really works well with the base mediatedness. Okay, so let's do a bad example now. It's simple, but it's going to be bad. It's not going to work. And we'll see why a reaction might not work. And why did this work again is because chloride's a good leaving group. So let's try what was the worst leaving group now. Carboxylic acid is the worst leaving group. Let's try the same exact thing. And say, can we make this amide the same way? Okay, so now we have a horrible leaving group. A horrible leaving group that's actually kind of acidic. It's a carboxylic acid. So the nitrogen cannot really kick off this leaving group. It can attack, and that will actually make this kind of thing. It can attack. It can attack, but it can't kick off the leaving group because the leaving group is bad. The OH is our desired leaving group. So, you know, you might lose your proton, just like always. Lose the proton on nitrogen. Now you're stuck. You cannot kick off this bad leaving group from the oxygen. Okay. And so the reaction cannot proceed. Okay. But what's the other thing that can happen? So this, we're kind of stuck here because the oxygen cannot kick off this leaving group. OH is a bad leaving group, right? Okay. And what's the other thing that can happen though? Rather than the nucleophile attack, the base can just take off the proton. Right? That's another thing that can happen. And now we're even more stuck, because now it's actually even worse of a leaving group. It's a carboxylate, right? And the carboxylate is not a leaving group at all, and so it can't go any further. Everything's just bad here. This is bad. Bad reaction. NR. Even no reaction. So put a big X in the arrow. This is just bad in multiple ways. What are the multiple ways that is bad? It's bad because even though the nucleophile could attack and even lose the proton, then you're stuck as a bad leaving group. And the other thing is maybe even more likely than the nucleophile attacking, the base can just take off the proton because it's acidic, and now you have a carboxylate, and this is bad also. So bad in multiple ways. And the net result is that the reaction doesn't go. This is not a good reaction. Okay? So this shows, what does this show you? It's like in order to do these reactions, you need a good leaving group. And hydroxy is not a good leaving group. You need a better leaving group like chloride. So there's going to be a couple ways to get around this. And one of them is that if we use the acid catalyzed reaction, we can get this to work sometimes. Okay? All right. So, what we're going to see is that we can use the base-mediated and the acid-catalyzed reactions in different situations. Let's get into number 7 now. Preparation and NAS of acid chlorides. Preparation and NAS of acid chlorides. Okay, and acid chlorides we're going to see are a very versatile carboxylic acid derivative. Very versatile. By that I mean you can convert an acid chloride into any of the other derivatives. We can convert an acid chloride into any of the other derivatives. Now that makes it really useful because it's like I can convert this into an anhydride, I can convert this to an ester, I can convert this to an amide, I can also convert it to a carboxylic acid. So acid chloride is versatile, right? Okay, so the first thing about acid chlorides is how to make them. How to make. How to synthesize a carboxylic acid, acid chloride. How do we do it? So this will be a reaction of the carboxylic acid with this reagent, which you've learned before. The name of it, what's the name of it? It's SO, S double bond O, ClCl, called thionyl chloride. You do know about this reagent because you learned about it. What did you use it for before? As early as Organic 1, the way to convert like an alcohol to a chloride was SOCl2. Thionyl chloride, the same reagent, SOCl2. So in this case, we're converting a carboxylic acid to an acid chloride using thionyl chloride. Okay, so the way to do this reaction is it almost will look like the acid catalyzed NAS. I'm going to take the lone pair on oxygen, attack sulfur, and kick off a chlorine. Lone pair of oxygen, attack sulfur, kick off a chlorine. Okay? See what we got now? Okay, and this is actually an RSCC. The overall reaction will be NAS, and we could say it's closer to the acid catalyzed NAS than the base mediated one. Okay, so we have an RSCC. Let's see the resonance structure. Cool. There's our resonance structure, carbocation right there. Okay. And what usually happens to carbocations? Things attack them. And what's going to do the attacking here? Well, initially we kicked off a chlorine, so we got chlorine around. Chlorine's going to do the attacking. Cl- is going to attack the carbocation. I'm going to draw the carbocation kind of above, just for space. Okay, so now the chloride attacks the carbocation, and what do we got now? So now we have this, okay? And let's go back, okay. So now we have this, and now it's actually very simple. Oxygen swings in, kicks everything off, and that gives you the acid chloride. Okay, so oxygen kicks everything off and makes SO2 goes away. Let's draw it up here. Okay, you have your protonated acid chloride now, and loss of proton minus H plus. It gives us the final product. Okay, so what gets kicked off of this? You kick off SOCl2 as a gas, so the SOCl2 gas goes away, and you also lose a chloride. Okay, and later you lose another H plus to give the final product. You lose the proton off the protonated acid chloride, and then final product is the acid chloride. Okay. And so that was the full mechanism. Oxygen attacks SOCl2, kicks off a chlorine, and then you have an RSCC, chloride attacks the RSCC, then just oxygen swings back, kicks everything off, kicks off the SOCl2, kicks off the oxygen, sulfur, and Cl, to kick off chlorine and SOCl2, and to give us the final protonated acid chloride, lose a proton, and there we go. So that's how you make an acid chloride. Okay, so it's a very easy reaction. You just take the carboxylic acid, SOCl2, and get an acid chloride. Okay. It's less common, but you can also make acid bromide. Acid bromides can be made the same way. With the, well, I guess the issue is bromine's usually more expensive than chlorine, so anything that uses bromine costs a little bit more. Nobody really uses acid bromides that often, but nevertheless, because you learned also, how do we convert an alcohol to a bromide? We learned this in Organic 1 also. How do you convert a alcohol to a bromide? And the answer is PBr3, right? PBr3. So how do you think we make an acid bromide from a carboxylic acid? Also from PBr3. And it's going to be this very similar type of mechanism than what we just did for thionyl chloride. Okay. So I'll do this one quickly. Oxygen attacks phosphorus, kicks off a Br. Now we have an RSCC. What do? We resonate. from the acetyl bond O upward. And next, what happened? It's not a big deal that I'm using irreversible arrows here. Most likely they are reversible except the last step, which kicks off the gas. It's okay to be a little sloppy with those. I'm using the irreversible arrows right now. But yeah, BR attacks. Okay, that's easy, just like before. Okay, and so now the last step, this is where the actual acid bromide gets formed essentially. Same thing like before, oxygen kicks in, this kicks off and kicks off a BR. And now you get a protonated acid bromide and lots of proton. Okay, so if you wanted to draw this with reversible arrows, I think it would be I'll just adjust this. It's reversible, reversible. This step is irreversible because the formation of the phosphorus double bond oxygen thing is a very stable molecule, so it's considered irreversible. Okay. And then the loss of a proton is reversible. Again, that's not a real big deal. On all quizzes and things, it's okay to use the irreversible arrows, these kind of arrows, okay? But indeed, there are definitely reactions that are reversible. Okay, so that's acid bromides. Now, how can we maybe use acid chlorides plus a carboxylic acid to make an anhydride? It's very easy, given the fact that the chloride is a very good leaving group. This reaction goes really well. So this will be a base-mediated NAS. Reaction. This is, and almost all of the reactions of acid chlorides will be base-mediated NAS. So it's really easy. Let's envision this. Let's convert this to an anhydride. We want to convert this to an anhydride. First thing that we want to do is make it into an acid chloride. How do you convert a carboxylic acid to an acid chloride? Well, we just learned how. It's SOCl2. Okay? And I am going to now, I want to make this into an anhydride. I'm going to make it into a anhydride where it's going to be butyl on one side, 1, 2, 3, 4, acetyl on the other. So how might that look? Okay, so that's what the product's going to look like. And given that this is a really good leaving group, this is very, very easy. Okay? All right, and so Well, the only thing though about this that makes it different from a normal base-mediated NAS, this happens to be a acidic functional group. Okay, this is very acidic. So rather than this just attack, we're just going to take off the proton first. You're only going to see this when carboxylic acid is a nucleophile. So base takes proton and then pushes onto the to make a carboxylate. Okay. Because remember what normally happens with acid, with base-mediated NAS. Normally, nucleophile attacks, lose a proton, and then it just falls apart and makes the product. The difference here is, rather than nucleophile attack, lose proton, we're going to lose proton first to make this. And then it's going to be a very simple mechanism. This attacks, electrons go up. There's our intermediate. I forgot we should probably mention this. This is called a tetrahedral intermediate. So we're going to see this over and over, how basically electrons go up and then electrons either immediately or like in the next step go down, kick off a leaving group, and we're done. But this intermediate is called a tetrahedral intermediate. And why is it tetrahedral? We're going to see this kind of intermediate over and over and over and over and over in this chapter. Tetrahedral because what's the hybridization? It's sp3, right? We went from sp2 to sp3, and then when this kicks off, we're back to sp2. sp2, sp3, sp2. And it's a tetrahedral intermediate, okay? And that's because of the sp3 hybridization. Okay, cool. So this is one simple example of something you can do with an acid chloride. We're going to see that you can convert acid chlorides to any of the other intermediates through something like this, through a mechanism very similar. So I can convert them to esters, I can convert them to amides, I can convert them to anhydrides, as we just showed. Oh wait, I actually made a little boo-boo. I have an extra carbon there, so let's just, to fix it, let's just erase this. Yeah. There we go. Okay, so there, now it's cool. Because we had 2 carbons here, 1, 2, we have 2 carbons there, and now we have 2 carbons there. But the point I was trying to make is that you can interconvert, and you can convert an acid chloride to any of the other derivatives I showed you, esters, amides, anhydrides, and carboxylic acids, using these kind of reactions. Okay? And this is one example of how to make an anhydride. And the way to make an anhydride is really make an acid chloride, convert a carboxylic acid to an acid chloride, and then throw in a carboxylic acid in a base-mediated NAS reaction via the tetrahedral intermediate to the product. Now the book emphasizes another way to make anhydrides. I will not test you on this or quiz you on it. I'm just going to mention it because the book does. It's not, I would say, the most interesting way to make anhydrides. So, not on quiz. So if you're studying for the quiz, don't worry about me asking you about this. But what the book shows, for example, is if I have a dicarboxylic acid, like that, and I cook it really hot, 300 degrees Celsius. You know, that is unusual temperature. Out comes the anhydride. Okay, and also water. And what's the boiling point of water? Well, it's 100 degrees, so we're really cooking this stuff really hot, kicking out water, which is 100 degrees. So the water vaporizes, and that kind of drives forward this equilibrium. So it's going to be a series of equilibria reactions followed by kicking out water, and that's irreversible, right? So anyway, I will just show one mechanism for this. It's not that bad. I just don't think it's that exciting. That's why it would never be on a quiz or an exam. But just have the oxygen attack kind of as a nucleophile. There's no base around or anything. So if that oxygen attacks, okay, and we proton transfer maybe to the oxygen that's going to be a leaving group. Then we get that, and now we just kick this off. That's it. It's going to be kind of equilibrium, and then this is irreversible because we're kicking off something that's going to instantly turn into a gas at 300 degrees. So it's actually not that bad of a mechanism. You're going to learn a whole bunch of mechanisms this chapter, so this is not a high priority one. Okay, so not on quiz. This is just another way to make anhydrides. Basically cook carboxylic acids or like a dicarboxylic acid to super high temperatures, and that gives you anhydrides with the kicking off of water. Okay. Okay. We're on letter C. And so, acid chlorides are very versatile, acid chlorides are a very versatile derivative. By derivative, I mean carboxylic acid derivative, and by versatile, I mean you can convert them to all the other things really easily. So what I'm going to show you is a little chart that really helps memorize this and to visualize all of the different reactions. So acid chloride, I'm going from most reactive to least reactive. Which, remember, it goes acid chloride, anhydride, ester, that's R prime, so it can be a methyl or an ethyl are often used. And then we got the amide, carboxylic acid. Okay. So what we're going to see, we already showed you how to go from an acid chloride to an amide, right? How did that work? Remember, that was one of the first reactions we learned. It was a base-mediated NAS. Acid chloride to amide was really easy because all we did was we threw in the amine. All we did is threw in the amine, and we used a base, pyridine, B dot dot, right? That's how we went from an acid chloride to an amide. What I'm trying to say, though, then, is if I want to go from anything that's on the left side of this chart to anything on the right, it's really easy. So acid chloride can be converted to an anhydride, which we just saw that, right? What do we use as our nucleophile? That was the electrophile. We used essentially a carboxylic acid, and then we were able to make an anhydride, right? And what if we want to make an ester? If we want to convert an acid chloride to an ester, what do you think we're going to react with? Maybe this, but don't just have OR prime, it's going to be HOR prime, so an alcohol. The alcohol plus acid chloride makes an ester. How do we make an amide? Use the amine plus a base, and that makes, goes from acid chloride to amide. How do you think we're going to go from acid chloride to a carboxylic acid? If we want to destroy an acid chloride and make a carboxylic acid, it would usually be water. Water is the nucleophile, and the mechanism is very easy. We'll show that in a bit. Okay, and just as well, anhydride can make anything to its left. So an anhydride, I'll draw this a little differently. I'm going to make my arrow a little displaced. I'm going to say an anhydride is also a reactive derivative with a good leaving group, just like a chloride's a good leaving group. This is actually a good leaving group too. It can only make things to its right. So the anhydride can be converted to an ester really easily, or to an amide really easily, or to a carboxylic acid really easily. And a ester can be converted to an amide really easily, or to a carboxylic acid really easily. Okay? And an amide can be converted to a carboxylic acid relatively easily. It turns out that an amide is actually a pretty stable functional group and a little bit unreactive, but there's ways to do this. So it looks like it's really easy to go from left to right. Very easy to go from left to right. And these are all essentially base-mediated NAS on the top here. Okay, base-mediated NAS is how it's pretty easy to go from left to right. Now there's going to be a little bit of wiggle room, but this is actually a pretty easy chart to visualize, I think, right? Now if it's very easy to go from left to right, then how do we go from right to left? Well, that's hard because that's a bad leaving group, right? You have the worst leaving group in the world. But we learned that there is a way to go from a carboxylic acid to an acid chloride, right? And it wasn't using base-mediated NAS. It's actually closer to acid-catalyzed NAS. So this is, we'll say, I'm going to put a little squiggly because it's not exactly the same. It's acid-catalyzed NAS, because we didn't have acid, we didn't use H+, but it kind of had that sort of mechanism, acid-catalyzed NAS, where the oxygen attacked thionyl chloride, oxygen attacked SOCl2, right? Okay. All right. And what else? I'm also going to mention that it is very easy to go from an alcohol to an ester. A carboxylic acid. A carboxylic acid to an ester. And this is definitely an acid catalyzed NAS. And this is essentially treating a carboxylic acid with H+ and a alcohol gives you an ester. This is definitely acid catalyzed NAS, as I showed the mechanism. Acid catalyzed NAS, H+ catalyzed NAS. Okay, and this also has a name called the Fischer Esterification. So this is a classic reaction discovered, I don't know, 1800s or earlier, that converts a carboxylic acid in the presence of H+ and alcohol to an ester, and it's called the Fischer Esterification reaction. Okay, so that plus alcohol plus acid makes ester. It's an easy way to make esters. If you're in the Organic 2 lab, I guess the labs aren't in operation, but this is one of the experiments you'll learn in Organic 2 lab. is students make a whole bunch of different esters using this reaction. Carboxylic acid plus alcohol plus a little bit of sulfuric acid, acid catalyst, it creates esters. Okay, great. And let's see. Okay, so we're still in the acid chloride section, So I'm trying to kind of emphasize that, yeah, acid chlorides can be converted to any of these other different things. It's basically through base-mediated NAS, right? And that I can kind of go from left to right really easily with base-mediated NAS. If I'm going from right to left, it's kind of this acid-catalyzed NAS. And the main two examples are SOCl2, right, which was carboxylic acid to the acid chloride, and then the Fischer Esterification. Okay, but let's just show another example. Let's say, I don't know, let's make an ester. Let's go from acid chloride to ester. We have not done that yet. Acid chloride to ester. Let's see. So let's draw a nice acid chloride. Benzoyl chloride. It's a benzene and a C double bond O and Cl. Let's react with a cyclohexanol and pyridine, PYR dot. So is this acid catalyzed or base mediated? Well, no acid. And generally speaking, with acid chlorides, it's always base mediated NAS. You can imagine what the product is. We're just going to replace the chlorine with the alcohol, and we're going to make an ester. So in this example, the left is benzene and aromatic, the right's not. It's a cyclohexane, like cyclohexanol. Okay. What's the mechanism of base-mediated NAS? This is a very simple mechanism. Don't touch the base yet. The base is not involved yet. Okay? Nucleophile attacks. Remember? That was first thing is nucleophile attacks. Don't forget the positive charge on the oxygen. What's the next step? Base does something. Now base takes the proton. I just flipped it around a bit. Uh-oh. And that's not a benzene. Sorry, my bad. Okay, so nucleophile attacks, electrons go up, base takes the proton off of where the nucleophile was, the alcohol proton. Now we have, both of these are considered tetrahedral intermediates. This is the one that's going to collapse to give the product. But yeah, that's a tetrahedral intermediate, that is also. So I could write that for tetrahedral intermediate. Okay, so they're both, there's little arrows. Tetrahedral intermediate, tetrahedral intermediate. There are two tetrahedral intermediates. How do we finish this reaction off? O minus kicks off chlorine. Cool, done. That's how you convert an acid chloride in the presence of an alcohol and a base to an ester. It's a pretty easy example. Okay. Okay, so let's show another example of an acid chloride reaction, and we talked about how amines react with acid chlorides. amines react with acid chlorides to make amides, right? So this is a good leaving group, that's a good nucleophile, and there's the base. This is a base-mediated NAS, a normal base-mediated NAS. We've only saw one kind of abnormal one, which was when the nucleophile is a carboxylic acid. And then the abnormality was that we would actually use the base to take the proton off first. Okay, this pKa is insanely high. It's like 35. So that is not an acidic proton. Amine pKa's are really high, and so the base can't just rip off a high pKa proton like this, because it's actually a very weak base. Okay, let's think about the product. Nitrogen is going to kick off the chlorine, and so it's going to look like this, right? And then you'll have the nitrogen thing. Okay, so yeah, the amine will kick off the acid chloride to make an amide. And what's the mechanism? Like I said, the base does not take off that proton. This is a high pKa proton, so this is not going to happen. What's going to happen is the nucleophile is going to attack the carbonyl to make the initial tetrahedral intermediate. Okay, so the nucleophile attacks, kicks electrons up. What do we got on there? O minus, nucleophile attacks, got O minus. Okay, this is maybe your first tetrahedral intermediate. First tetrahedral intermediate. And what happens next? Now the base takes the proton off nitrogen. Okay, base takes proton off nitrogen. Okay, and now what? Again, these base-mediated NAS mechanisms are really easy, right? Now you have your second tetrahedral intermediate, and it's ready to give the product. Now it swings down, kicks off the leaving group, done. That's a pretty easy mechanism, right? Okay. Very cool, very cool. So that's another example of a base-mediated NAS of an acid chloride. We should, oh yeah, one more thing. What's the pKa of this proton? Obviously, do you think it's higher or lower than the initial one? Is it more acidic or less acidic? Well, when it's positively charged on nitrogen, it's very, very acidic. We went from pKa 35 to, I actually don't know the exact number off the top of my head. It may be 8 or something. Maybe 8. I'm guessing. It might be 8 or 9 or something. Yeah, 8. Yeah. And pKa. When you think about the difference of 35 and 8, that's not a huge number. It's, what is it, a 27 or something, yeah. 27. And but it's really exponential. So the difference in acidity between that NH2 and this guy, which is pKa 8, this NH, is, if it's a difference of 25, it's really 10 to the 25, so it's 1 followed by 25 zeros. So that is insanely more acidic, right? That's the point I'm trying to make, is generally speaking, if you have a low acidity proton on your nucleophile, high pKa, like a amine or also alcohol, the base will not just take off that proton. You don't have a strong base. This can only take stuff off that's maybe less than 10 or something like that. And so, you know, this proton's pKa 8, so the pyridine can take that off. And so generally speaking, in the normal base-mediated NAS, the base does not do anything until after the nucleophile attacks. Nucleophile attacks, you got your tetrahedral intermediate, base takes the proton, and then it swings down, kicks it off, and takes the product. In the case of carboxylic acid, which we showed earlier, carboxylic acid to make anhydrides, the pKa is like 4. So it's a highly acidic proton. Pyridine rips off the pKa 4 proton. And then that's the only case where pyridine actually takes the proton off first. Okay, hopefully that was clear. Okay, so I'm going to just really quickly stop with esters. I just want to mention esters briefly. Reaction overview of esters. What I want to do is just quickly show the two common ways to make them from like an acid chloride. Prep from acid chloride. Because we learned that already, how to make an ester from an acid chloride. So let's just make one. We'll do this easy one. And we're going to draw it a little differently because that's fine. Okay, so now we're just having alcohol and an acid chloride and a little bit of base, maybe pyridine or something. You can imagine what the product will be. It'll just be the oxygen kicks off the chlorine, and we don't have to show the mechanism just to show the product, I hope. It's really just going to be the ester of the left piece with the right piece here. So it's just this. This is called isoamyl acetate, and this smells intensely like bananas. So this is one of the, I talked about Organic 2 Lab, how you make some esters. Well, this is one of the esters you would make in the Organic 2 Lab, and it's a very intense banana smell. It is actually the chemical that gives banana their characteristic smell. Okay, so isoamyl acetate is a really cool, nice smelling compound. Okay, let's just blast through this mechanism. It's a base-mediated NAS. This is very easy, right? Should be getting good at this now. Tetrahedral intermediate. What does base do? Takes out the proton. Here's your second tetrahedral intermediate. There's your product. So the mechanism is very easy with these base-mediated NAS, right? Okay. So lastly, I just want to show the Fischer Esterification because it's really easy also. We're still on esters. And I just want to get through this mechanism. It's not that big of a deal. It is, though, it is acid catalyzed NAS, which we haven't done that much of, but you know, I showed it in general terms initially. This is the Fischer Esterification. Okay, and it's a way to do this reaction with acid catalysis to make a whole bunch of esters. Let's and remember, you know, when I showed our big chart, I was like A, B, C, D, E, you know, how it was like going from left to right was always base mediated, right? But if we go right to left, it would be acid catalyzed, H plus cat. And we showed that Fischer is one of them. It was from the carboxylic acid to the ester using acid catalyzed NAS. So that's, I just want to show that real quick. And we'll do the same example we just did. And then it'll be done. Alright, so let's show how to do this with acid catalyzed NAS. Okay. So I'm drawing it this certain way that really helps us see the mechanism. This is totally in equilibrium, and I'm going to use equilibrium arrows every step of this. The big thing is we're turning alcohol plus a carboxylic acid to the ester and water. Okay, and we'll do the mechanism, and we'll talk a little bit more about it next time. But what do you think the first step is? We already mentioned that with acid catalyzed reactions, C double bond O, maybe the oxygen grabs the proton, and that's what happens. Protonate the carboxylic acid. I'm going to draw it over here. And what is the next step? You make an RSCC. So let's show the resonance form. So the electrons go up onto oxygen. Okay, so this is kind of like old chapter 17 stuff, right? Protonate something, resonate. Now we see the other resonance form. And what do you think is going to attack this positively charged carbocation? Maybe the alcohol, because we got to obviously form a bond from oxygen to carbon. Let's do it now. So I'm going to just grab this alcohol and attack. Alcohol attacks the carbocation, alright? That's not that bad, huh? Hopefully not that bad. Now I'm just going to rearrange this a little bit to orient it closer to the final product. So we got methyl, what else do we have? Yeah, it's that, I guess. Okay, and this is essentially our tetrahedral intermediate, right? Okay, so yeah, we protonated, we resonated, we had alcohol attack. Now we got this. What happens after nucleophilic attack? We're going to move a leaving group for move a proton from one atom to another. So it's PT. Okay. So there's weird equilibrium areas that are bent. Gets a little congested there. I just moved from that oxygen to the top oxygen arbitrarily. Now we're ready to kick off our leaving group. So now I use the other oxygen to kick it off, and we're basically done then. So now it looks very close to the product. Now we have our protonated ester. Lose a proton. You can say minus H plus, and we're done. So this is the Fischer Esterification, and this will be where we stop. I just wanted to show it. I'm glad we got through this because it's an important reaction. Real quickly, what did we do? We protonated the carboxylic acid to make an RSCC and a carbocation. Alcohol attacked it. Then, like always, or very, very commonly, after nucleophilic attack, we proton transfer from one oxygen to the other. I picked the top one. You could pick the other one if you like. And then we just kick off the water that's, water is a good leaving group, and kicks it off. And then we're done. We lose a proton and we're done. That is Fischer Esterification. It's a really nice mechanism, and definitely something we show in the quizzes from time to time. So be ready for it. Very lastly, as an equilibrium, I'm going from A plus B to C plus D. If I want to go from left to right, I would maybe have one of these in excess, or maybe the alcohol in excess. It's like I want to make this product, I would maybe have this or this in excess. If I want to go the other way, if I want actually have an ester and I want to cleave it, if if I have an ester and I want to cleave the ester back to these two pieces, how could I do that? I could do the same exact reaction in the excess of water. So I could have like 100-fold excess of water, and then it would actually cleave the ester back to these guys. And that's the point, that this is totally reversible. You can go from left to right, if I have one of these in excess, or I can go from right to left, maybe if I have water in excess. Okay, that's it. Have a wonderful weekend.